This is the general background of Beijing Jiaotong University magnesium explosion. It occurred on 26 December 2018 at Beijing Jiaotong University, which soon claimed the lives of 3 of its students that were carrying out sewage treatment experiment. The cause of the incident is said to be due to improper handling of dangerous chemical, hydrogen gas generation, magnesium dust explosion, and staff negligence. Response from officials include Emergency Department, Fire Services, Public Security, and Ministry of Education, in which 12 personnel were disciplined. And lastly, nationwide, it is later required to improve the safety system and further laboratory training.
This incident involved magnesium powder and phosphoric acid. Magnesium powder is highly flammable when dispersed in air and can form an explosive dust cloud. When magnesium reacts with phosphoric acid or moisture, hydrogen gas is produced, which is highly combustible. Mechanical stirring may have dispersed the magnesium dust and generated sparks, leading to ignition. The explosion was likely caused by the rapid combustion of magnesium dust and hydrogen gas, producing magnesium oxide and a sudden release of heat and pressure.
This is the properties of chemicals involved in the incident, which are magnesium and phosphoric acid. Magnesium is a silver grey metallic powder that is highly reactive when heated and combustible, posing an ignition risk in the presence of flame, sparks, or heat. It reacts with water to produce hydrogen gas, which contributes to its fire and explosion hazard. Phosphoric acid is a clear colorless liquid that is highly soluble in water. It reacts violently with strong bases and oxidizing agents, and also reacts with metals to release hydrogen gas, increasing the risk of fire under certain conditions. Magnesium powder and phosphoric acid pose significant laboratory hazard due to their physical and chemical properties. Magnesium powder presents a fire and explosion risk, particularly when reacting with acids, as flammable hydrogen gas is released. Inhalation of magnesium dust may cause respiratory tract irritation, while contact with the eyes and skin can result in mechanical irritation or particle embedding. Phosphoric acid, on the other hand, is corrosive and can cause severe skin and eye burns. Inhalation of its vapor or mist may irritate the respiratory system. Additionally, its reaction with metals can generate flammable hydrogen gas, and combustion may produce toxic fumes, further increasing safety risks.
Now let's move to the hazard and health effect of magnesium powder. From a toxicological perspective, magnesium metal has a low level of systemic toxicity when absorbed by the human body. However, significant health risks arise when magnesium is present in the form of fine powder or dust. Inhalation of magnesium powder may irritate the nose, throat, and lungs, leading to coughing, breathing difficulty, and general respiratory discomfort. Direct exposure of the eye to the magnesium particle can cause redness and irritation, and in more severe cases may result in damage to the cornea. According to the mature safety data sheet, magnesium powder is classified as a hazardous substance primarily because of its high reactivity and flammability rather than due to its intrinsic toxicity. Okay, now is the MSTS risk, accident case, and safety measure. According to the MSTS, magnesium powder poses a significant fire and explosion hazard due to its finely divided form, which allows it to react rapidly with oxygen in the air. The powder can easily ignite when exposed to heat, spark, friction, or static electricity, and it burns at extremely high temperature while emitting intense white light that can seriously damage vision. Magnesium also reacts strongly with water and acids, producing hydrogen gas, which is highly flammable and explosive in confined spaces. This hazard was demonstrated in the Beijing Jiaotong University laboratory incident, where improper handling and failure to follow an MSTS guideline led to hydrogen gas accumulation and subsequent ignition. To reduce this risk, the MSTS recommend the use of Class D fire extinguisher for metal fires, along with proper ventilation, grounding, suitable personal protective equipment, correct storage condition, and adequate training for personnel handling magnesium powder.
There is a regulation related to the use of chemicals in laboratories. There are two types of regulation. First is Malaysian regulation, second international guidelines. For Malaysian, we have 5, which is OSHA 1994, second USCE CHH 2000, class 2013, FMA 1967, regulation 2005. For international guidelines, we have WHO, World Health Organization. International Labour Organization, ILO also we have. This regulation provides a legal framework for managing chemical risks, protecting laboratory use, preventing workplace accidents, and they also have ensured consistency in laboratory safety practice across different institutions. There are 7 failures in safety management that led to the accident. First is no proper risk assessment. Second, unsafe handling of hazardous chemicals. Third, poor control of ignition sources. Fourth, inadequate ventilation. Fifth, lack of supervision. Sixth, insufficient safety training. And lastly, poor emergency preparedness. These failures occurred simultaneously and were not addressed in a timely manner, which significantly increased the risk of a serious accident.
These are the impacts of the accident on people's health and environment. The impacts of the accident have killed at least 3 students who were taking part in the experiment. The public security, the director of the research project, and also the manager of the laboratory was investigated for criminal negligence. Then the Ministry of Education and Beijing Jiaotong University have took further action by punishing and expelling 12 officials from the university. In the meantime, psychological counseling services were offered to the teachers and students who suffered trauma from the accident. Moving on to the lessons learned from the accident. Number 1. We can establish storage sites for hazardous chemicals that meet safety requirements and seriously investigate and punish illegal storage of hazardous chemicals. Number 2. We can establish a centralized post-process management platform for hazardous chemicals and strengthen the management of the purchase, transportation, storage, and use of hazardous chemicals. Number 3. We must select the appropriate experimental method and formulate the experimental safe operation specifications. The experimental equipment should meet the requirements of fire and explosion protection. And last but not least, the relevant personnel should receive corresponding training before the experiment, including the risks that may exist, the experimental operation procedures, and the precautionary measures in the emergency.